हेलो एन्ड नमस्ते। आज चाहिँ च्याप्टर 4 हेर्छौँ हामी चाहिँ होइन। च्याप्टर 4मा के छ त भन्दाखेरि रियल वर्ल्ड डाटा रिप्रेजेन्टेसन बुझिन्छ। त्यसपछि वर्किङ विथ इमेज, त्यस पछाडि 3D इमेज, भोलोमेट्रिक डाटा, 3D इमेज, भिडियो पनि पर्छ ओके यसमा। रिप्रेजेन्टिङ टेबुलर डाटा, वर्किङ विथ टाइम सिरिज। पेज नम्बर 70बाट समरी हेर्ने भयो भने 102 हुन्छ, 31 पेजको। In the previous chapter, we learned that tensor are the building blocks for data in PyTorch. A neural network takes tensor as input and produce tensor as output. In fact, all operation within a neural network and during optimization are operation between tensors. And all parameters, for example, weights and bias in a neural network are tensor. Having a good sense of how to perform operations on tensor and index them effectively is central to using tools like PyTorch successfully. Now that we know the basic of tensors, your dexterity with them will grow as you make your way through the book. Here is a question of that we can already address. How do we take a piece of data or video or a line of text represent it with a tensor in a way that is appropriate for training a deep learning model? This is what we will learn in this chapter. We will cover different type of data with a focus on the type relevant to this book, and so how to represent the data as tensor. Then we will learn how to load the data from the most common on this format and get a feel for those data types structures, so we can see how to prepare them for training a neural network. Often our raw data won't be perfectly formed for the problem we will like to solve, so we will have a chance to practice our tensor manipulation skills with a few more interesting tensor operation. In each section in this chapter will describe a data type and will come with its own data set. While we have structured the chapter so that each data type builds on the previous one, feel free to skip around a bit if you are so inclined. Okay, we will be using a lot of image and volumetric data throughout the rest of the book. Since there are common data types and they reproduce well in this book format, we will also cover tabular data, time series, and text, as those will also be of interest to a number of our readers. Since a picture is worth 1,000 words, we will start with the image data. We will then demonstrate working with a three-dimensional array using medical data that represent patient anatomy as a volume. Next, we will work with tabular data about ones, just like that we will find in a spreadsheet. After that, we will move to order tabular data with a time series dataset like by sharing program. Finally, we will dip our toes into text data from Jane Austen. Text data retains it order aspect with introduce the problem of representing word as arrays of numbers. In every section, we will stop where our deep learning researchers will start. Right before feeding the data into a model, we encourage you to keep those datasets. They will consume excellent material for when we start learning how to train neural network model in the next chapter. Working with images, the introduction of convolutional neural network revolutionized computer vision. Okay, and image-based system have since acquired a whole new set of capabilities. Problems that requires complex pipeline of highly tuned algorithmic building blocks are now solvable on precedented level of performance by training into a network using paired input and desired output examples. In order to participate in this revolution, we need to be able to load an image from common image format and then transform the data into a tensor representation that has the various part of the image arranged in the way PyTorch expects. An image is represented as a collection of scalars arranged in a regular grid with a height and a width. In pixel, we might have a single scalar per grid point, the pixel, which will represent a grayscale image. So grayscale image पछि त एक one dimensional भयो, मतलब one channel को भयो, or multiple scalar per grid point which we typically represent different colors RGB भइहाल्यो हैन. As we saw in the previous chapter, or different feature like depth from a depth camera. Scalars representing values at different pixel are often encoded using 8-bit integers as in consumer cameras. Okay, in medical, scientific, and industrial application, it is not unusual to find higher numerical precision, such as 12-bit or 16-bit. This allows a wider range or increased sensitivity in cases where the pixel encode information about a physical property like bone density, temperature, or depth. So adding color channel, we mentioned color earlier. There are several ways to encode color into numbers. The most common is RGB, red, green, blue. Okay, where a color is defined by three numbers representing the intensity of red, green, and blue. We can think of a color channel as a grayscale intensity map of only the color in question. Similar to what we would see if you looked at the scene in question using a pair of pure red sunglasses. Figure 4.1, okay, shows a rainbow where each of the RGB channel captures a certain portion of the spectrum. The figure is simplified in that it highlights things like the orange and yellow bands being represented as a combination of red and green. Okay, rainbow, red, green, blue. Okay, the red band of the rainbow is brightest in the red channel of the image, while the blue channel has both the blue blend of the rainbow and the sky as a high intensity. Note also that the white cloud are highly intensity in all three channels. Loading an image file. Image comes in several different file formats, but luckily there are plenty of ways to load images in Python. Let's start by loading PNG image using a Imagio module. Code को PL1 chapter को 4 मा छ अरे. Let's say code को PL1 को chapter 4. Image, which image dog? यसमा के भएको छ नि, this is something under statement color model. So input imagio, okay. Image IRR imagio.imread. So save read गरेको. Let's check. ल्याब च्याप्टर आजको चाहिँ च्याप्टर पार्ट 1 च्याप्टर 4 रिनेम पार्ट पार्ट 1 च्याप्टर 4 कनेक्ट सो इम्पोर्ट इमेज हो छ कि छैन हेरौँ न सो छ IMGARR इमेज डकको एउटा इमेज हाल्नु पर्यो आई थिङ्क हिजो डकको इमेज छ कि छैन अपलोड डक MGARR equal to image हो image हो imread यसमा चाहिँ पासमा dog1.jpg त्यसपछि imgarr.save 4000 6000 by 3 को we will use Imagio throughout the chapter because it handles different data types with a uniform API. For many purposes, using Torch Vision is a great default choice to deal with image and video data. We go with Imagio here for somewhat lighter exploration. Torch Vision हेर्नुपर्छ नि त्यही काम लाग्ने भएपछि त त्यही गर्नुपर्छ नि कति भन्ने क्या अथरलाई At this point, image is a NumPy array-like object with 3 dimensions, 2 spatial dimension width and height, and a third dimension corresponding to the red, green, blue channel. Any libraries that outputs NumPy array will suffice to obtain a PyTorch tensor. The only thing to watch out for is the layout of the dimension. PyTorch module dealing with the image data request tensor to be laid out at channel हुन्छ height हुन्छ नि width हुन्छ तर टेन्सर module के गर्छ height width and channel okay change the layout we can use the tensor permute ले गर्न सकिन्छ permute मा के गर्दिने हैन 1 2 अनि 0 गर्दिए नि भइहाल्छ ओके 1 2 0 ओके हामीलाई ल्याउनु पर्ने चाहिँ पहिला के अरे पछाडिपट्टिको ल्याउनु पर्ने पछाडिपट्टिको च्यानललाई अगाडि ल्याउनु पर्यो भने चाहिँ के हुन्छ त यदि यसलाई 3 लाई अगाडि ल्याउनु पर्ने हो भने त त्यसो भने त यसलाई परम्युटमा 2 च्यानल आयो 01 परम्युट 01 गर्दै हुन्छ होला so okay dimension to get the appropriate layout given an input tensor height width the channel as obtained previously we get a proper layout by having channel and two first and then channel 0 and 1 so like here so so img is equal to torch dot from numpy read गर्ने हो numpy read गरेर चाहिँ img arr त्यस पछाडी torch torch किन भएन भन्दा इम्पोर्ट टर्च गरेर इम्पोर्ट टर्च गरियो so यही गरे out is equal to image img.permute permute गरेर मिल्छ होला त्यसपछि out को सेप हेर्दिउँ न त so 3 4000 6 okay 4000 6000 अगाडि 3 channel आइहाल हो okay सेभ भन्यो we have seen this previously but note that this operation does not make a copy of the tensor data instead out uses the same underlying storage as image and only plays with the size and the stride information at the tensor level This is convenient because the operation is very cheap. But just as a head up, changing a pixel in img will lead to a change in output. Okay, so change in image will affect in output. किन त एउटा सेमै हुन्छ भनेको हो. सो डिप कपी यताउता युज गरे भए चाहिँ बरु चाहिँ बल्ल नयाँ भन्थ्यो. ओके. Note also that other deep learning framework use different layers. For instance, original TensorFlow keep the channel dimension last, resulting into height with channel. Okay, layers are layout. It now supports multiple layout. Okay, this strategy has pros and cons from a low level performance standpoint. But for our concern, it does not make a difference as long as we shape our tensor properly. So far we have described a single image. Following the same strategy we have used for earlier data types to create a data set of multiple images to use as an input for our neural networks. We store the image in a batch along the first dimension to obtain an NCHW. So N is the we have used for earlier to create data set of multiple images. Okay, so N is a multiple image like N हो. So number हुने भयो, त्यसै color हुने भयो, height हुने भयो, width हुने भयो. As a slightly more efficient alternative to use a stack to build our tensor, we can pre-allocate a tensor of appropriate size and fill it with image loaded loaded from the dictionary, like so. Okay, batch size 3, so batch is equal to torch into 0 journey. Okay. So batch size is equal to 3 गर्ने. So batch is equal to batch torch dot zeros 0 सम्म चाहिँ batch size को दिने. batch size त्यस पछाडि batch size को भयो, त्यसपछि channel 3 को 256 okay 256 so this is d type चाहिँ के राख्नु खोजेको यसले torch dot unit uint it. This indicates that our batch will consist of 3 RGB images, 256 pixel in height and 256 pixel in width. Note that the type of tensor we are expecting each color to be represented as an 8-bit integer, as in most photographic format from standard consumer camera. We can now load all images, PNG images from an input directory and store them in the tensor. What is that? Download data chapter 1 को 4 image and cat. कतिवटा सर 3टा त रहेछ नि. ओके download save cat 2 cat 3 तीनटा इमेजलाई इमेज क्याटाले एउटा इमेज बनाएर हाल्दिउँ न त के जान्छ र. ओके न्यू फोल्डर image cats. Okay, so import OS data directory is equal to image cats underscore बनाएगी स्लैश है underscore सब लगाएर थियो ओके त्यस पछाडि फाइल नेम्स इज इक्वल टु okay name or name in os.list directory list data dir names file names file names चेक गरी हेरौँ पहिला ओके आइरहेछ फाइल नेम्स भइहाल्यो लास्ट इज if os.path dot split x name minus 1 is equal to dot png okay png चाहिएगा for I file name in enumerate file names filenames file names img arr is equal to image io dot imread os.path dot join data directory र file name त्यस पछाडि img tl ट्रान्सपोज गर्न त लगाएर torch dot from numpy मा img arr हाल्यो त्यस पछाडि फर्मेट गर्ने ओके img t is equal to img underscore t dot formute गर्दा 2 लाई ल्याउने 1 लाई 0 ल्याउने 0 ल्याउने 1 लाई ल्याउने त्यसपछि img underscore t is equal to image t minus last को 3 वटा here we keep only the first 3 channel sometimes image also have alpha channel indicating transparency but our network only once RGB okay यो नलेख्नु रहेछ त्यो पनि batch I is equal to img d torch has no from batch is not defined batch माथि थिएन र batch batch ओके सो हामीले batch को एरे बनाइरहेको छौँ हैन ब्याच त बनाएको हेर्नु त्यसपछि ब्याच किन फेल भइरहेको त ब्याच बनाएर हामीले कतै हिजो यसमा छैन त ब्याच वाइ ब्याचको साइज 3 बनाएको थियो ब्याच यस्तो बनाएको थियो अनि यसमा चाहिँ रन हुने छ मेरोमा चाहिँ रन नहुन खोज्ने वाइ name batch is not defined okay एउटा एरे बनाइदिउँ न त टेक्स्ट लिएर के गर्न खोजेँ मैले active assignment ब्याचकै हामीले एरै बनाएको होइन यो माथिको ब्याचले किन लिएन त लिनु पर्ने त्यसले हँ त्यसले किन लिएन ब्याचको त एउटा ऊ बनाएको छ त टेन्सन जेरोस बनाएको छ यत्तिकै बन्द छ त्यत्तिकै लिस्टमा बनाउनु पर्ने हो र नगर्नु पनि जस्तो लाग्छ र खाली खाली काम गर्छ त batch I is equal to image t, so list assignment index out of range. के कुरा एक्स्ट्रा लेखेर त्यही नै कपी त हो इमेज अंदर स्क्वायर क्याट छ यति होला यदि यो हुँदैन भने कन्ट्रोल F9 ओके अहिले फेरि रन भयो यो चाहिँ हैन कन्ट्रोल F9 रन भइरहेको ए भगवान रन अल गर्न पनि पागलै हो कि पागल म चाहिँ त्यतिखेर we normalize the data we mentioned earlier that neural networks okay Okay, normalizing the data. We mentioned earlier that neural networks usually works with floating points tensor as their input. Neural networks exhibit the best training performance when the input roughly from 0 to 1 or from -1 to 1. This is an effect of how your building blocks are defined. So a typical thing we will want to do is cast a tensor to floating point and normalize the value of the pixel. Casting to floating point is easy, but normalization is trickier as it depends on what range of the input we decide should lie between 0 and 1, okay, or -1 to 1. One possibility is to just divide the values pixel by 255, okay. The maximum representable number in 8-bit unsigned, so batch is equal to batch dot float batch dot float batch divided by 255, okay. Normalize गर्नलाई batch is equal batch divided by 255.0, okay. Divided by another possibility is to compute the mean and the standard deviation of the input data and scale it so that the output had 0 mean and unit standard deviation across each channel. So n channel is equal to base dot shape 1. So shape 1 गर्दाखेरि के आउँछ? shape 1 0 गर्दाखेरि so size आउने होला नि height. Let's check गरेर हेर्दिउँ न. And ब्याच साइजमा ब्याचको सेप भनेपछि त पहिला त ब्याच साइज छ, त्यसपछि च्यानल छ, त्यसो भने त ठिकै हो. एन्ड च्यानल्स इज इक्वल टु ब्याच डट सेप 0 मा ब्याच साइज छ, 1 मा च्यानल छ. ठिक छ. फर सी इन रेन्ज सी च्यानल so mean is equal to torch dot mean यो फ्लोटमा छ, पहिले टाइप कास्ट गर्नु पर्दैन. ब्याच डाउन सबै सिले std is equal to torch dot std standard deviation. स्लाइसिङ गर्दाखेरि रोज कलम सबै अल रोज, त्यस पछाडि सिले. ओके, त्यस पछाडि ब्याचमा सीमा इक्वल टु ब्याच सी माइनस mean less divided by standard deviation. Okay. Here we normalize just a single batch of image because we do not know it how to operate on the entire data set. In working with image, it is a good practice to compute the mean and standard deviation on all the training data in advance, and then subtract and divide by these fixed pre-computed quantities. We saw this in the preprocessing of the image classifier in section 2.1.4. okay, this is preprocessing. So we can perform several other operations on inputs such as geometric transformation like rotation, scaling, and cropping. This may help with training or may be required to make an arbitrary input conform to the input requirements of a network, like the size of the image. We will stumble on quite a few of these strategies in section 12.6. For now, just remember that you have image manipulation option available. Okay. 3D image volumetric data. We have learned how to load the represent 2D image like the ones we take with a camera. In some contexts, such as medical image application involving say CT computed tomography scans, we typically deal with sequences of images stacked along with head to foot axis, each corresponding to a slice across the human body. In CT scan, the intensity represents the density of the different parts of the body: lungs, fat, water, muscle, and bone, in order of increasing density, mapped from dark to bright when the CT scan is displayed on the clinical workstation. The density at each point is computed from the amount of X-ray reaching our detector after crossing through the body, with some complex math to deconvolve the raw sensor data into the full volume. Cities have only a single intensity channel similar to a grayscale image, and this means that often the channel dimension is left out in native data format. So similar to the last section, the raw data typically has 3 dimensions. By stacking individual 2D slices into a 3D tensor, we can build volumetric data representing the 3D anatomy of a subject. Unlike that we saw in the figure 4.1, the extra dimension in figure 4.2 represents an offset in physical space rather than a particular band of the visible spectrum. Okay, top, middle, bottom. सो 3D भोल्युमेट्रिक भयो भने कसरी हेर्ने भन्ने कुरो. ओके, सो ब्रेन. So part two of this book will devoted to tackling a medical imaging problem in the real world. So we won't go into the details of medical imaging data formats. For now, it's suffice to say that there is no fundamental difference between a tensor storing volumetric data versus image data. We just have an extra dimension depth after the channel dimension. So leading to a 5D tensor of images. So this is the best size, channel depth, height and width. So loading a specialized format. Let's load a sample CT scan using bold red function in the image IO module, which takes a directory as an argument and assembles all digital imaging and communication in medicine file in a series in a numpy 3D array. Code chapter 4 को volumetric city. डाटा कहाँ लिएको छ यार, डाटा कुन हो फेरि, सबैभन्दा पहिला त डाटा हेर्नु पर्यो. इमेज एन्ड क्याट होइन, भोल्युमेट्रिक यही होला फेरि. राम्रो यति रहेछ. Two lungs, two lungs 3.0. यत्रो रहेछ त डाटा. डाउनलोडै गरेर राख्नु पर्ने भयो. कति टाइम लाग्ने भयो. ओके. च्याप्टर 4 भनेर च्याप्टर 4 राखेँ, तर यसलाई चाहिँ कन्टिन्यू गर्दै जाऊँ कि नयाँ बनाऊँ. यसलाई त्यसरी चेन्ज गरौँ नि त. च्याप्टर 4 त्यस पछाडि इमेजवाला थियो, यसलाई इमेज राखौँ, न्यू बनाउँदैछु म. क्यान्सल सेभ. मलाई चाहिएको त डाटा. च्याप्टर 4 को भोल्युमेट्रिक को यो भित्र के छ या यत्रोलाई कसरी हाल्ने हो. त्यो लास्ट छ. सेभ भयो हैन. न्यू ओपन नोटबुक न्यू बनाइदिनु पर्यो. पार्ट 1 च्याप्टर 4 को भोल्युमेट्रिक डाटा भोल्युम मात्र लेखेर राख्छु. यसमा अपलोड गर्नलाई डाटा पहिला गरौँ. पहिला एउटा बनाउनु डाटा भनेर. डाटा अपलोड डाटा च्याप्टर 4 को यसको सबैलाई कति समय लगाउने छ. इमेज आयो. टर्च छ कि छैन, इम्पोर्ट टर्च पनि गरेर राखौँ. सो डिरेक्टर पाथ भनेको चाहिँ मैले राखेको चाहिँ डाटा सो भोल array is equal to image io dot bolded bolded directory path थियो directory path थियो DICOM यसको के छ DCM रहेछ नि त DCM छ त्यसरी भोल ARR dot save सबै रेड भइसक्यो नि त्यही पनि अपलोड गरेर भइसकेको रहेछ ठ्याक्कै मिलेछ 99 15 99 15 हो कतिवटा छ यसको Hmm. 99 512 512 ठिक छ ओके त्यसैले as we do in section 4.1.3 that layout is different from what PyTorch expect due to having no channel information, so we will have to make room for the channel dimension using unsqueeze हाल्ने सो unsqueeze ले के गर्छ भन्दाखेरि एउटा हालिदिन्छ तर एन्ड डिम चाहिँ कुनमा हालिदिन्छ फेरि जिरो डाइमेन्सनमा जिरो डाइमेन्सन भनेको अगाडि अनि ब्याच जान्छ यसमा त के आइरहेछ 99 भनेको त ऊ भएन यो डेप्थ भयो होला हाइट भयो होला विड्थ भयो होला सो च्यानलको लागि ठाउँ त बनाउनु पर्यो भनेपछि भोल इज इक्वल टु ओके torch डट फ्रम numpy भोल डट ARR डट फ्लोट गरिदिनु भयो नभए डट टाइप गरेर torch डट फ्लोट गरिदिनु भयो torch TORCH डट फ्लोट यो गरे पनि हुन्छ एउटै हो सो भोल इज इक्वल टु torch डट अन SQUEEZD अनस्क्विज गर्यो अनस्क्विज भोलमा गर्ने हो भोलमा गरिसकेपछि एनडिम भनेको डिमेन्सन भनेको जिरोमा थप्ने एउटा अनस्क्विज गर भनेको होइन त्यसपछि भोल डट सेभ सो 199 512 512 okay. At this point, we could assemble a 5D dataset by stacking multiple volume along the batch direction. Just as we did in the previous section, we will see a lot more city data in part 2. Representing tabular data. यति मात्र गर्न रहेछ दुःख गर्नु परेको हे भगवान The simplest form of data we will encounter on a machine learning job is sitting in a spreadsheet. Okay, CSV file or database, whatever the medium it is a table containing one row or sample where columns contains one piece of information about our sample. At first we are going to assume there is no meaning to the order in which sample appears in the table. Such a table is a collection of independent samples, unlike a time series, for instance, in which samples are related by a time dimension. Columns may contain numerical values like temperature at specific locations or labels like a string expressing an attribute of a sample like blue. Therefore, tabular data is typically not homogeneous. Different columns don't have the same type. We might have a column showing the weight of apples and another including their color in a label. Okay, PyTorch tensor on the other hand are homogeneous. Information in PyTorch is typically encoded as a numbers, typically floating points. though integer types and boolean are supported as well. Okay. This numeric encoding is deliberate since new neural networks are mathematical entities that take the real numbers as input and produce real numbers as output through successive application of matrix multiplication and nonlinear functions using a real dataset. Our first job as a deep learning practitioner is to encode heterogeneous real old data into a tensor of floating point numbers ready of consumption by a neural network. A large number of tabular datasets are freely available on the internet. So, see, for instance, GitHub Go, K share 0301 or some public dataset. Let's start with here. Right here. Copy, Control P, Control V, enter public dataset. Agriculture is okay. Architecture, biological. There is the let's start with something fun. Wine. The wine quality database is freely available, containing chemical characterization of samples of Vinho Verde, a wine from North Portugal, together with the sensory quality score. The dataset for wine can be downloaded here. Control C. Database से maintain कर रहा है क्या मतलब विदेशी लेयर्स जैसे के लेयर्स चलो CSV बनाओ copy of data on the user table one so यसको यहाँ यसबाट डाउनलोड यसमा पहिले डाउनलोड छ त यार डाउनलोड छ नि त सिधै डाटाबाट हेरे भइगयो त टेबलर वाइन सिधै टेबलर वाइन होला यसलाई अपलोड हान्दै भइहाल्यो नि अब दुःख किन गर्छ नि बेकार सो यसैमा अपलोड हान्दा धेरै झ्याउ लाग्यो घरमा Control C नेम पनि कपी गरेर हाल्नुहोस् काम लाग्छ For convenience, we also created a copy of data on the deep learning the table The file contains a comma separated collection of values organized into 12 columns preceded by a header line containing the column name. The first 11 column contains values of chemical variables and the last column contains the sensory quality score from 0 to 110. These are the columns name in the order they appear in the dataset. So the possible machine learning task on this dataset is predicting the quality score from chemical characterization alone. Don't worry. Though machine learning is not going to kill wine testing anytime soon, we have to get the training data from somewhere. As we can see in figure 4.3, we are hoping to find a relationship between one of the chemicals column in our data and quality column. Here we are expecting to see quality increase as sulfur decreases. Yes, it's sulfur pH quality. Okay, sulfur decreases गर्दाखेरि क्वालिटी इन्क्रिज हुन्छ जब सल्फर डिक्रिज हुन्छ ओके सल्फर बढ्दै गयो क्वालिटी गर्दै गयो त्यस्तो कुरा So before we can get to that, however, we need to be able to examine the data in a more usable way than opening the file in text editor. Okay, pandas username anta यसपालि numpy pandas. Okay, let's see how we can load the data using Python and then turn it into a PyTorch tensor. Python offers several options for quickly loading a CSV file. Three popular are CSV module that ships the Python with Python, NumPy, Pandas. The third option is the most time and memory efficient. However, we'll avoid introducing additional library in our interjectory just because we need to load a file. Since we already introduced NumPy in the previous section, the PyTorch has excellent NumPy interoperability. We'll go with that. Let's load our file and turn the resulting NumPy array into a PyTorch tensor. So import CSV गर्दैछ क्या. So NumPy लाई read गर्नेलाई छ. Import numpy as np import csv. त्यसपछि wine path गर्दा यसो गर्दा कन्ट्रोल भी अहिलेको राखिराखेँ. यसमा csv लेख्दै भइहाल्यो. So wine numpy is equal to np dot load txt wine path बाट d type is equal to np dot float 32 delimiterमा ओके. त्यसपछि skip rows is equal to 1 र पहिलोलाई skip गरिदिने हो. wine numpy आयो. Here we just prescribe that the type of 2D array should be 32-bit floating point. The delimiter used to separate values in each row, and the fact that the first line should not be read since it contains the column names. Let's check that all data has been read. So col list is equal to next iteration csv dot reader open wine path delimiter is equal to wine numpy dot save बाह्र 1 2 3 4 5 6 7 8 9 10 11 12 0 बाट 11 सम्म. And proceed to convert the numpy array to PyTorch. So it is सीधै from numpy गर्दै भइहाल्छ नि, के गर्नु पर्दैन यसलाई त. wine q is equal to torch dot from numpy गरेर wine numpy गरिदियो भने त पुगिहाल्छ. numpy के गर्नुपर्छ र wine q र यसको save wine q dot d type SHA ये मिस्टेक भयो. Runtime interrupt execution. Restart session. Restarting Python 3. Control F9 हान्दिने. Connected भयो नि. Connected भएन, Control F9. Okay, आयो torch 48 98 12 float 32. Okay, continuous ordinal categorical value. At this point, we have a floating point torch.tensor containing all the columns, including the last, which refers to the quality score. Continuous, ordinal, and categorical values. We should be aware of three different type of numerical values as we attempt to make sense of our data. The first kind is continuous value. These are the most intuitive when represented as numbers. And they are strictly order. They are strictly order, and our difference between various values has a strict meaning, stating that package A is 2 gram heavier than package B, or that package B come from 100 miles farther away than A, has a fixed meaning regardless of whether package A is 3 gram or 10, or if B came from 200 miles away or 2000. If you are counting or measuring something with units, it's probably a continuous value. The literature actually divides continuous values further in the previous example. It makes sense to say something is twice as heavy or three times farther away. So those values are said to be a ratio scale. The time of the day, on the other hand, does not have the notion of difference, but it is not reasonable to claim that 6 o'clock is twice as late as 3 o'clock. So time of the day only offer an interval scale. Now we have ordinal values. The strict ordering we have with continuous values remains, but the fixed relationship between values no longer applies. A good example of this is ordering a small, medium, or large string, with small map to the value 1, medium to large 3. This is ordinal. The large string is bigger than the medium. In the same way, 3 is bigger than 2, but it doesn't tell us about how much bigger. If we were to convert our 1 to 3 to the actual volume, say 8, 12, 24 liquid ounces, fluid ounces, then we will switch to being interval values. It is important to remember that we can't do math on the values outside of ordering them. Trying to average large 3 and small 1 does not result in a medium drink. Finally, categorical values have neither ordering nor numerical meanings to their values. These are often just enumeration of possibilities. Assign arbitrary numbers. Assigning water to 1, coffee to 2, soda to 3, and milk to 4 is a good example. There is no real logic to placing water first and milk last. They simply need distinct values to differentiate them. We can assign coffee to 10 and milk to -3, and there will be no significant change, though assigning values in the range of 0 to n-1 will have advantage. For one hot encoding and the embeddings, we will discuss in section 4.5.4. Because the numerical values bear no meaning, they are said to be a nominal scale representing scores. We should treat the score as a continuous variable, keep it as a real number, and perform a regression task, or treat it as a level and try to guess the level from the chemical analysis in a classical task. In both approaches, we will typically remove the score from the tensor of input data and keep it in a separate tensor, so that we can use the score as the ground truth without it being input to our model. So data is equal to when q गरेर all rows गर्यो, त्यसपछि -1 भनेको -1 भनेको लास्ट -1 लास्टको गर्ने लास्टलाई गर्ने भनेको लास्टलाई हटाउने भन्नु खोजेको. डाटा इज इक्वल टु वान क्यु स्लाइसिङ गर्यो एउटा अलको रोज, त्यसपछि -1 यो लास्टको मान मात्र लिने भन्नु खोजेको, रोजलाई हटाउने भन्नु खोजेको. क्या डाटा डट सेभ. So 11 12बाट 11 आयो. Okay. Target is equal to 1 q सबै लिने, त्यसपछि -1 लास्टको एउटा मात्र लिने भनेको त्यो चाहिँ टार्गेट हुने भयो. टार्गेट डट टार्गेट र टार्गेटको सेप हेर्ने. Okay, if we want to transform the target tensor into a tensor of levels, we have two options depending on the strategy or what we use the categorical data for. One simply is to treat level as integer vectors of scores. Okay, सिधै यसलाई के भन्छ अरे लङमा लयो. ओके, यसलाई के गर्यो भन्दाखेरि जस्ट 0.7.0 6.0 67 गराइदियो. अरू के त गरेको छ र. टार्गेट इज इक्वल टु 1 क्यु सबै लियो, सबै लिएर माइनस लास्टको एउटा लियो, डट लङ गर्यो, टार्गेट गर्यो. Float int logos. If targets were string labels like wine colors, assigning an integer number to each string would let us follow the same approach. Okay. अब आएको छ one hot encoding. The other approach is to build a one hot encoding of the scores. That is, encode each of the 10 scores in a vector of 10 elements, which all elements set to 0 but one at a different index for each score. This way a score of 10 will be mapped into a vector. Okay, score of 5 into 5 को ठाउँमा भनेको 5 ठाउँमा 1 राखिन्छ नि 0 1 2 3 4 5 गर्ने and so on. Note that the fact that the score corresponds to the index of the non-zero element is purely incidental. We could shuffle the assignment and nothing would change from a classification standpoint. There is a marked difference between the two approaches. Keeping one quality score is a integer vector of score induce and ordering of on the score, which might be actually appropriate in this case, since a score of 1 is lower than a score of 4. It also induce some sort of distance between score. This is the distance between 1 and 3 is the same as the distance between 2 and 4. If this holds for our quantity, then great. If on the other hand scores are purely discrete, like grapes variety, one hot encoding will be a much better fit, as there is one implied ordering or distance. Okay, one hot encoding is also appropriate for quantitative score when fractional values in between integer score. Okay, fractional values between integer scores like 2.4 make no sense for the application or when the score is either this or that. Okay, we can achieve one hot encoding using the scatter method, which fills the tensor with values from a source tensor along with the indices provided as argument. Okay, target on hot is equal to torch dot zeros. यसमा त उ दिनु पर्यो, साइज दिनु पर्यो, टार्गेटको सेप दिनु पर्यो. टार्गेटको सेप 0 मा, टार्गेटको सेप के छ यो यसमा 0 त्यत्रो लामो, अनि के को बिटमा दिने 10 सम्म. ओके, टार्गेट 1 hot dot scatter 1 target dot on squeeze 1 dimension ma. Okay, 1.0. मान्छे स्केटरमा लयो, 1 गऱ्यो टार्गेटको अनस्क्विजलाई 1 गऱ्यो, अनस्क्विज भनेको एउटा थप्यो। ओके सो 1.0 नारुहोदो। Let's see what scatter underscore does. First, we notice that it changes in with an underscore. As we learned in the previous chapter, this is the convention in PyTorch that indicates the method will not return a new tensor but will instead modify the tensor in place. Argument from scatter are as follows. The dimension along which the following two arguments are specified: a column tensor indicating the indices of the element to scatter, or tensor containing the elements to scatter, or a single scatter to scatter one in this case. In other words, the previous invocation reads for each row take the index of the target level which coincides with score in our case and use it as column index to set the volume 1.0. The end result is a tensor encoding categorical information. The second argument of scatter, the index tensor requires to have the same number of dimensions as the tensor we scatter into. Since target one hot has 2 dimensions only, okay, 896, we need to add an extra dummy dimension to target using on squeeze. So target on squeeze is equal to target dot on squeeze 1. On squeeze 1 the call to unsqueeze add a singleton dimension from a 1D tensor of 4898 elements to a 2D tensor of size 4898 into 1. Without changing its content, no extra elements are added. We just decide to use an extra index to assess the elements. This is we assess the first element of targets as target 0 and first element of his unsqueeze counterpart as target unsqueeze 00. Okay, PyTorch allows us to use class indices directly as target while training neural networks. However, if we wanted to use the score as a categorical input in the network, we have to transform it into a one hard coded tensor. Categorical input one say one headed tensor and when to categorize. Now we have seen ways to deal with both continuous and categorical data. Now you wonder what the deal. What the deal is with the ordinal case discussed in the earlier sidebar. This is no general recipe for it. Most commonly, such data is either treated as categorical, losing the ordinal part and hoping that maybe our model will pick it up during training. If we only have a few categories, or continuous introducing an arbitrary notion of distance. We will do the later. For the weather situation in figure 4.5, we summarize our data mapping into a small flow chart in figure 4.4. So column contain continuous data, yes गर्ने, use values directly गर्ने, no ordinal no, so yes ordinary priority, okay, no categorical data, yes. Let's go back to our data tensor containing the 11 variables associated with the chemical analysis. We can use the function in the PyTorch tensor API to manipulate our data in tensor form. Let's first obtain the mean and standard deviation for each column. So data mean is equal to dot mean data pass गर्यो त्यसमा dimension 0 मा dimension 0 मा त्यसपछि data mean के आउँदो रहेछ हेर्दै ओके विभिन्न आइरहेछ त्यसपछि नेक्स्ट data variance हो var is equal to data dot variance data dimension is equal to 0 data variance torch. Okay, torch. So data normalized is equal to normalized is equal to so data minus data where divided by torch dot sqrt स्टैंडर्ड वेरिएंस निकालेगा इसका रूट कर फाइन्डिङ थ्रेसहोल्ड हामी कतिमा छौँ 4.3.6 4.3.6 सो फाइन्डिङ द थ्रेसहोल्ड पछाडि वर्किङ विथ टाइम सिरिज आउँदो रहेछ So finding threshold. Next, let's start to look at the data with an eye to seeing if there is an easy way to tell good and bad wines apart at a glance. First, we are going to determine which rows in target correspond to a score less than or equal to 3. So it is okay. Bad index is equal to target greater or equal greater less or equal to 3. So bad index dot say. Okay, bad indexes is equal to target less or equals to 3. Bad indexes, that's it. Bad indexes dot d type, bad indexes dot sum. So यतिवटा चाहिँ bad indexes को सेप छ त्यसपछि bad indexes data type boolean आयो tinsor is equal to tinsor चाहिँ 20. Okay, something. Note that only 20 of the bad indexes entries are said to be true. By using a feature in PyTorch called advanced indexing, we can use a tensor with data type torch.bool to index the data tensor. This will essentially filter data to be only items or row corresponding to true in the indexing tensor. Bad indexes tensor has the same shape as our targets with the values of false or true depending on the outcomes of the comparison between our threshold and its element in the original target tensor. So bad data is equal to data like slicing at the bad index le. So bad data dot shape area ni. So B-Soda is a bad index. Note that the new bad data tensor has 20 rows, the same as the number of rows with true or the bad index tensors. It retains all 11 columns. So now we can start to get information about ones grouped into good, middling, and bad categories. Let's check the mean of each column. So bad data is equal to data target less or equals to 3. It's a bad data भयो. This is already mid data is equal to data target greater or equals to 3. Okay, and लगाउनु पर्ने हो greater or equal to 3 and target less than 7 भनेको चाहिँ middle range को good data is equal to data so target greater or equals to 7. These are the good data. Bad mean equals to torch dot mean bad mean bad data. Mid mean is equal to torch dot mean mid data. This is very good. Good mean is equal to torch dot mean good data. Okay. Dimension dim. Okay, dimension bandi. So dim equals to 0. Dim equals 0. Dim equals 0. So we want 0 0. So for I args in enumerate zip okay, call list call list ma bad main made main good main okay 20 6.2 6.2 either thing 6.2 of that for math I slash args cannot switch from automatic field numbering to manual field subscription के छुट्यो base 6.2.0 ये छुट्यो fix acidity को 7.6 badmin good volatile acidity को 0.33 bad सब bad है खासै राम्रो छैन it looks like we are on something here. At first glance, the bad wine seems to have higher total sulfur dioxide. Bad has sulfur dioxide. Bad has sulfur dioxide. Okay. 0.47 sulfate sulfur dioxide. Okay, 170. Total sulfur dioxide, okay. 170 140 okay. जति सल्फर डाइअक्साइड कम भयो त्यति भयो राम्रो भन्ने कुरो त्यहाँ भन्न खोजेको नि हो we could use a threshold on total sulfur dioxide as crude criteria for discriminating total good wine from bad ones. Let's get the indexes where the total sulfur dioxide column is below the midpoint. We calculated earlier like this, like so. Total sulfur range mid चाहिँ 141.82 so योभन्दा माथिको गुड त्योभन्दा माथिको ब्याड भन्न खोजे हो अनि टोटल सल्फर डाटा इजिकलमा 6 वटा लिने भन्न खोजेको लेट्स चेक दियौँ सो टोटल सल्फर threshold 41.83. Six. Hmm. उसको गलती लिखिए हमारे साथ उसको गलती से टॉर्च टॉर्च computes less than on your LT on less than गर्नेला other element is the second argument can be a number or a tensor whose shape is broadcastable with the first argument. So each tensor गरिदियो भने false to true भनेर चाहिँ यो भन्दा सानो छ यो भन्दा false 3 is less than 4 true 4 is less than 4 false less than LT गर्दो रहेछ ओके बुझ्यो LT मा के बस्छ नि त total sulfur data total sulfur threshold predicted index shape this means our threshold implies that just over half of all the wines are going to be high quality. Next we will need to get the indices of actually good wines. So actual indexes is equal to target greater than 5. Since there are about 500 more actually good ones than our threshold predicted, we already have hard evidence that it is not perfect. Now we need to see how will our prediction line up with actual ranking. We will perform a logical and between our prediction indexes and the actual good indexes. Remember that each is just an array of zeros and ones, and use that interaction of ones in arrangement to determine how well we did. N matches is equal to toss dot sum actual indexes and prediction indices. Okay, N गरिदिउँ न त. N matches is equal to toss dot sum actual indexes and predicted. That item. Equatorial ACTUL actual. We got around 2000 ones, right? Since we predicted 2700 ones, this gives us a 74% chance that if we predict a wine to be high quality, it actually is. Unfortunately, there are 3200 good wines, and we can only identify 60% of them. Well, we got what we signed up for. That's barely better than random. Of course, this is all very naive. We know for sure that multiple variables contributing to one quality and the relationship between the values of this variable and the outcome, which could be actually sure. Rather than a binarized version of it, yeah, is likely more complicated than a simple threshold on a single value. Indeed, a simple neural network will overcome all of these limitations as we will a lot of other basic machine learning method. We will have the tools to tackle this problem after the next two chapters. Since we have learned how to build our first neural network from scratch, we will also revisit how to better graduate our result in chapter 12. Let's move to another data types for now. So working with time series. Oh, 70बाट स्टार्ट गरेको 87 17 पेज भयो 1.5 घन्टा नि भइसकेछ 17 पेज पढ्नलाई मलाई 1.5 घन्टा लाग्यो भनेपछि गरेर 3 घन्टा लाग्ने रहेछ मलाई 13 पेज छ okay in the previous section we covered how to represent data organized in a flat table. As we noted, every row in the table was independent from others. Their order did not matter. Going back to the wine dataset, we could not have had a year column that allowed us to look at how wine quality evolved year after year. Unfortunately, we don't have such data at hand, but we are working hard on manually collecting the data samples bottle by bottle. Stuff for our second edition. In the meantime, we will search to another interesting data set, data from Washington DC bike sharing system, repeating the hourly content of rental bikes in 2011-2012 in the capital bike share system, along with weather and seasonal information available here. Okay. Our goal will to take a flat 2D dataset and transform it into a 3D one as shown in the figure 4.5. So day 1, day 2, day 3, day of the day, time of the day, weather, temperature, humidity, wind speed, bike count, etc. So day by day को खप्टिरहेको हुन्छ ओके त्यसैले भन्दा टाइमको इन्डिपेन्डेन्ट ओके डे 1, डे 2, डे 3 भएको अनुसार ओके So adding a time dimension in the source data, each row is a separate hour of data. Figure 4.5 shows a transposed version of this to be a better fit on the printed page. We want to change the row per hour organization so that we have one axis that increases at a rate of 1 day per index increment and another. Okay, for index increment and another axis that represents the hour of the day, independent of the date. The third axis will be our different column of data, weather, temperature, and so on. Let's load the data. So time series bikes.ipny को रे यसको लागि डाटा कुन फेरि हेर्नुपर्छ डाटा ipx time series bikes भएन डाटा चाहिँ let's see the data bike sharing data set यो होला so fixed hour CB लाई रेडी गरेको हो यसलाई पनि अब टाइम सिरिजले न्यू बनाइदिउँ जे हो नगरिकन बाइक सिरिज फ्याक्टर त नै फ्याक्टर दियो part 1 chapter 4 time series टाइम सिरिजमा के छ भन्दाखेरि पहिला इम्पोर्ट गरौँ इम्पोर्ट टर्च गरेर राखौँ त्यसपछि इम्पोर्ट numpy एज np गरेर राखौँ त्यस पछाडि bikes डट numpy इज इक्वल टु np डट लोड txt गर्यो त्यस पछाडि हामीले के गर्ने रहेछौँ आवर फिक्स्ड हो आवर फिक्स csv त्यसपछि यसलाई रिड गर्दाखेरि डी टाइपमा np डट float 32 मा delimiter इज इक्वल टु यसमा यो गरिदिएका छौँ त्यसपछि स्किप रोज एउटा स्किप रो नि त्यस पछाडि त्यस पछाडि कन्भर्टर्समा 1 such that lambda x okay float x 10 BIKS 1 ओके कन्भर्टरको यो हैन ओके यो हो त converter specified one column which is invalid for number of field 1 कपी गरेर हाल्दिउँ त के मिस्टेक भएर रहेछ कन्भर्टरको केसमा केमा मेरो के थियो त एरर भएछ क्या यसमा एरर थियो होला साइड ओके बाइक्स भयो यहाँसम्म for every hour the data set reports the following variables index of report instant day of month day season spring summer fall winter चारवटामा ओके year 11 12 month 1 to 12 hour 1 to 24 holiday status holiday week of the day weekday working day status working day weather situation weather sheet clear means light rain snow heavy rain temperature in degree celsius perceived temperature humidity number wind speed number of casual risers number of registered users count of rental bikes. So in a time series dataset such as this one, rows represent successive time points. There is a dimension along which which they are ordered. Sure, we could treat each row as independent and try to predict the number of circulating bikes based on say a particular time of day, regardless of what happened earlier. However, the existence of an ordering gives us the opportunity to exploit causal relationship across time. For instance, it allows us to predict bike ride at one time based on the fact that it was raining at an earlier time. For the time being, we are going to focus on learning how to turn our bike sharing dataset into something that our neural network will be able to ingest in fixed size chunks. Okay, this neural network model will need to see a number of sequence of values for each different quantity such as ride count, number of day, temperature, weather conditions, and parallel sequence of size C stand for channel in neural network parlance. It's the same as column for 1D data we have there. Okay, and dimension represent the time axis here, 1 entry per hour. So shaping the data by time period, we might want to break up the 2-year dataset into wider observation period like days. This way we will have here the number of samples collection of sequence of length L L will be 24 1 per hour of the day. There is no particular reason why we must use chunks of 24 hours. Though the general daily rhythm is likely to give us patterns we can exploit for prediction. We could also use 7 into 24, so 168-hour block to chunk by week instead if we decide. All of this depends naturally on our dataset having the right size. The number of rows must be multiple of 24 or 168. Also, for this to make sense, we cannot have gaps in the time series. Let's go back to our bike sharing data set. The first column is index, the global ordering of the data. Okay, second is the date, and the sixth is the time of the day. We have everything we need to create a data set of daily sequence of ride count and other exogenous variables. Our data set is already sorted, but if it were not, we could use torch.sort on to it to order it properly. The version of the file we are using our fixed CSV has had same processing done to include rows missing from the original dataset. We presume that the missing hour and zeros bike active. They were typically in the early morning hours. All we have to do obtain our daily hour dataset is view the same tensor in batches of 24 hours. Let's take a look at the shape and the state at our bike tensor. Bike dot shape bikes dot stride. So यति एउटा रोज यति एउटा कलम 17 वटा कलम 17/1 को स्ट्राइडमा छ अरे. Okay, now receive the data and to have three axes: day, hour, and then our 17 columns. So view निकाले है यसबाट. daily bikes is equal to bikes dot view गर्यो -1. Okay, 20 को चाहिँ कभर गराएन कि है मैले. view bikes dot shape. bikes. So 730 को 24 घण्टाको भयो अरे 117 को भयो अरे. What happened here? First back.shape is 17, the number of columns in the back tensor. But the real crux of this code is to call a view, which is really important. It changes the way the tensor look at same data as contained in storage. As you learned in previous chapter, calling view on tensor returns a new tensor that changes the number of dimension and the striding information without changing the storage. This means we can rearrange our tensor at basically zero cost. Because no data will be copied, our call to view require us to provide a new shape for a return tensor. We use -1 as a placeholder for however however many indices are left given the other dimension, the original number of element. Okay. Remember also from the previous chapter that storage is a contiguous linear container for numbers, floating point in this case. Our back tensor will have each row stored one after the other in its corresponding storage. This is confirmed by output from the calls to bike.stride earlier. For daily bikes, the stride is telling that us that advancing by one along the our dimension, the second dimension, requires us to advance by 17 place. Okay, in the storage or one set of column. Whereas advancing along the dimension, the first dimension requires to advance by a number of elements equal to the length of row in the storage times 24, that is here 408, which is 17 into 24. We see that the rightmost dimension is the number of columns in the original data set. Then the middle dimension we have time split into the chunks of 24 sequence. Okay, sequential hour. In other words, we have now a sequence of allow in the C channels. To get our desired NCL ordering, we need to transpose the tensor. Okay. So daily bikes dot transpose to daily bikes shape so 1 को 2 मा 2 को 1 मा गराइयो हैन 730 into अब 17 को 24 hour मा गयो. Okay. Now let's apply some of the techniques we learned earlier to this dataset. Ready for training? The weather situation variable is ordinal. It has 4 labels: 1 for good weather and 4 for. Okay, let's check that as well. Hmm. The weather is okay, very is ordinary. We have okay for we could treat this variable as categorical, which label interpreted as labels or as continuous variable. If we decide to go with categorical, we will turn the variable into one hot encoded vectors and concatenate the columns with the dataset. In order to make it easier to render our data, we are going to limit ourselves to the first day. For a moment, we initialize a zero field matrix with a number of rows equal to the number of hours in the day and number of columns equal to the number of weather levels. So first day is equal to bike. So basically, then we scatter ones into our matrix according to the corresponding level at each row. Remember to use unsquished to add the singleton dimension as we did in the previous section. Hmm. So whether manhot dot scatter. Syntax. Our day scattered with weather one and ended with two. So that seems right. Last we concatenate our matrix to our original dataset using the cat function. So dot catenation. So bytes 24. And this will be a case where it is useful to go beyond the main path speculatively. Okay. Speculatively. We could also try to reflect like categorical but with order more directly by generalizing one hot encoding to mapping the ith of our four categories here to a vector that has one in the position 0 I and the zeros behind that are similar to the embeddings we discussed in chapter section 4.5.14. We could take partial sum of embeddings, in which case it might make sense to make those positive. As with many things we encounter in practical works, this could be a place where trying what works for other and then executing in a systematic fashion is a good idea. Here we prescribe our original bikes dataset and one hot encoding, uh, weather situation matrix to be concatenated along the column dimension, that is one. In other words, the columns of the two datasets are stacked together or equivalently. The new one hot encoded columns are uh, appended to the original dataset. For cat to succeed, it is required that the tensor have the same size along the other dimension, the row dimension in this case. Note that our last few four columns are 1 0 0 1 0, exactly as we would expect with a value of 1. We could have done the same with the received daily bike tensor. Remember that is SEP BCL, okay? Batch channel L180. Okay. Hmm. L is another layout just one. Let's create the zero tensor with the same B and L, but with the number of addition of column C. डेली वेदर इज हट कोड गरेर जेरोज बनाउने, डेली बाइकको सेपको जेरोमा, फेरि फोरमा डेली बाइकको सेपको डेली सेपको एकचोटि डेली बाइकको सेप हेरौँ त एकचोटि 740 24 17, ओके. जेरोमा 730 आउँछ, फोरमा 2मा चाहिँ 17 आउँछ, ओके. So daily weather one hot touch zeros daily bikes 0 को भाग आउने रे, त्यसमा 4 आउने रे, त्यसमा फेरि डेली बाइक्स, त्यसमा 2 आउने रे. डेली torch dot zeros. किन यसमा चाहिँ किन यस्तो चाहिँ कहाँ थियो यो? यहाँ कन्क्यानेट भइसकेपछि कहाँ हो त यो? टाइम सिरिज कति नम्बरको यार? ए त हो नि, ल यसलाई कपी पेस्ट गर्ने हुन्छ. के चाहिँ मिस्टेक छ र मेरो? डेली बाइक सेप, यहाँ सेप दिन म बिर्सेछ नि त नै मित्र हो. के मिसाएर नहेरेको. Then we scatter the one hot encoding into the tensor into the C dimension. Since this operation is performed in place, only the content of the tensor will change. Okay. Copy paste okay, to size for you. And we continue to remove the C dimension. We mentioned earlier that this is not the only way to treat our weather situation variable. Indeed, its level have an ordinal relationship, so we will pretend they are special values of continuous variable. We could just transform the variable so that it runs from 0.0 to 1.0. So let's do a run over it. So okay. Daily bikes as mentioned in the previous season, rescaling variables from 0 to 1 interval for okay -1 to 1. There is something we will want to do. All our quantitative variables like temperature, column 10 in our data. We'll see why later. For now, let's just say that this is a very simple for training purpose. There are multiple possible for rescaling variables. We can either map their presence to determine temp okay 10 वटा लियो हैन 10 वटा मात्र लिएको ओके टेम मिनिजल टच डट मिनको टेम लियो टेम म्याक्स टचको म्याक्स लियो डेली बाइक्समा इजिकल डेली बाइक्स माइनस मिनिमम घटाएर डिभाइडेड बाई म्याक्स माइनस मिनले गरिदियो क्या और subtract the mean divided by standard deviation. Okay. I will take this one. Normalize. In the latter case, our variable will have zero mean and unitary standard deviation. If a variable were drawn from a Gaussian distribution, 68% of the samples will sit in the okay -1 interval. Great, we have built another nice data set, and we have seen how to deal with time series data. For this RD horizon, it's important only that we got an idea of how a time series is laid out and how we can wrangle the data in a form that a network will digest. Our kinds of data look like a time series in that there is a strict ordering. Top two on the list, text and audio. We will take a look at next. Text next, and the conclusion section has links to additional example for audio. Representing text. अब पालो representing text. कहाँ से पुगे हामी representable data time series representing text. यसको छ ओहो यसको 5-6 प्रिन्ट पार्टहरु छ. राम राम राम. So deep learning एकचोटि टाइम एकचोटि यो पानी 2 घन्टा कम्प्लिट भएछ। So deep learning has taken the field of natural neural process by some, particularly using model that particularly consume a combination of new inputs and previous model output. These models are called RNN, recurrent neural network, and they have been applied with great success to text categorization, text generation, and automated translation system. More recently, a class of network called transformer uh, with a more flexible way to incorporate past information has made a big splash. Okay, previous NLP workloads were characterized by sophisticated multi-stage pipelines that are that are uh, that includes rules, encodings, the grammar of language. Now, state of the art train networks end to end on large corpora, starting from scratch, letting those rules emerge from the data. For the last several years, the most used automated translation system you available as service on the internet have been based on deep learning. Our goal is in this section is to turn text into something a neural network can process attention of numbers, just like our previous cases. If we can do that, and later chooses the right architecture for our text processing job, we will be in the position of doing NLP with PyTorch. We will see right away powerful how powerful this all is. We can achieve the state of the art performance on a number of tasks in different domains with the same PyTorch tools. We just need to cast our problems in the right form. The first part of this job is receiving the data. There are two particular intuitive levels at which networks operate on text. At the character level, by processing one character at a time, and the ord level, where individual ord are the finest grained entities to be seen by the network. The technique with which we encode text information into tensor form is same, whether we operate at the character level or the ord level, and it is not magic either. We stumbled upon it earlier one hot encoding. Let's start with a character level example. First, let's get some text to process. An imaging resource here is Project Gutenberg, a volunteer report to digitize and archive cultural work and make it available for free in open formats, including plain text files. If we are aiming at larger scale corpora, the Wikipedia corpora stand out. It is the complete collection of Wikipedia articles, contains 1.9 billion word and more than 4.4 million article. Okay, several other corpora can be found at the English corpora website. Okay, let's load Jane Augustine Pride and Prejudice from the Project Gutenberg website. Blah 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 blah. We'll just save the file and read it in the text. Okay, यसमा चाहिने डाटा कुनबाट रेड गरिरहेको छ जेन्स अगस्टिन. अब यसलाई नेक्स्टमा गरिदिने फेरि यसलाई क्लोज गरिदिने डिस्कन्टिन्यू डिलिट जा न्यू गर्ने यसलाई क्लोज गर्ने पार्ट 4 chapter part 1 chapter 4 NLP. यसमा अपलोड गर्नुपर्ने के हो त जेन अगस्टिनको यो with केही चाहिँदैन के भन्न सक्ने रहेछ नि त हौ ठिक छ open import के गर्नुपर्छ झन् सजिलो भने 10 text encoding UTF it HF text the left data read one hot encoding characters. There is one more details we need to take care of before we proceed encoding. This is a pretty vast subject and we will just touch on it. Every written character is represented by a code, a sequence of bit of appropriate length so that each character can be uniquely identified. The simplest such encoding is SK, okay, American Standard Code for Information Interchange, which date back to the 1960s. ASCII code 128 characters using 128 integers. For instance, the letter A corresponds to binary 11000001 or decimal 97, and the character B is K98 and so on. The encoding bits 8 bits, which was a big bonus in 1965. But 128 characters are clearly not enough to account for all the glyphs, accents, ligatures, and so on that are needed to properly represent written text in languages other than English. To this end, a number of encodings have been developed that uses a large number of bits as a code for a wider range of characters. That wider range of characters was standardized as Unicode that maps all known characters to numbers with a representation. In bits of those numbers provided by specific encodings. Popular encodings are UTF-8, UTF-16, and UTF-32, in which the numbers are a sequence of 8, 16, and 32-bit integers, respectively. String in Python 3.0 are Unicode string. Okay. We are going to one hot encode our characters. It is instrumental to limit the one hot encodings to a character set that is useful for the text being analyzed. In our case, since we loaded text in English, it is safe to use ASCII and deal with the small encodings. We could also make all the characters lowercase to reduce the number of different characters in our encoding. Similarly, we could screen out punctuations, numbers, or other characters that aren't relevant to our expected kind of text. This may or may not make a practical difference to a neural network depending on the task at hand. At this point, we need to parse through the characters in the text and provide a one hot encoding for each of them. Each character will be represented by a vector of length equal to the number of different characters in the encoding. This vector will contains all zeros except at the index corresponding to the location of the character in the encoding. We first split our text into the list of lines and pick an arbitrary line to focus on. Okay, line लाई स्प्लिट गर्ने न्यू लाइनले. सो लाइन्स इज इक्वल टु टेक्स्ट डट स्प्लिट केले स्प्लिट गर्ने भन्दा स्ल्यास एनले न्यू लाइनले. सो लाइन इज इक्वल टु लाइन्स 200. okay, line 200 and line. So impossible, Mr. Bennett, impossible when I am not acquainted with him. Okay. Later is equal to torch dot zeros. Import torch से गरेको थिएन नि त हो, चाहिन्छ पनि थाहा थिएन त हो. Import torch dot zeros line 128 letter T dot shape 7128. okay, note that letter T holds holds one hard encoded character per row. Now we just have to set on one on each row in the correct position so that each row represent the correct characters. The index where the one has to be set corresponding to the index of the character in the encoding. For I letter in enumerate line dot lower strip. Okay. For I letter in enumerate line dot lower dot strip letter index word order letter if word letter then 128 else 0 letter p I letter index equals 1. यो त क्यारेक्टरको रूपमा भएन इन्कोडिङ. ओके, यदि वान होल वर्डमा चाहिन्थ्यो भने डेफिनेसन क्लिन वर्ड्स इनपुट str. ओके, punctuation के भित्र चाहिएको रहेछ. एउटा डटमा चाहिएको, कमामा चाहिएको, यसमा के भन्छ अरे कमामा चाहिएको, सेमी कमामा चाहिएको, त्यसरी ठुलो ब्राकेटमा चाहिएको, त्यसपछि एक्सक्लेमेसन वाट 30 के हो त्यस 30 यो होला हुन्छ हो. सकिन्छ त्यति होला. टेक्स्ट के साइन रहेछ यो राम्रोसँग नदेखेको मैले. जस्तो लाग्थ्यो भने अलिक फरक छ जस्तो लाग्यो. मैले लेखेको र त्यो अलि रातो बुझ्नु त्यही पनि सो यसलाई टुक्राउँदो रहेछ. इम्पोसिबल मिस्टर बेनेट, इम्पोसिबल वेन आई एम नट acquainted with him. Okay, so ಇದು ಚುಟ್ಟಾದ್ರು ನೋಡ್ಬೋದು word by word. Next, let's build a mapping of words to indexes in our encodings. So word index, word list, sorted, set, clean, word. सबै टेक्स्टलाई गर्दैन word to back, word to index dict is equal to the word I for I slash word in enumerate word list len word to possible sorted. Note the word to index is now a dictionary with word as keys and an integer as a value. We will use it to efficiently find the index of a word as we hot encode it. Let's now focus on our sentence. We break it up into words and one hot encode it. Okay, and that is we populate our tensor with one hot encoded vector per word. We create an empty vector and assign in the one hot encoded values of the word in the sentence. Okay, OD underscore याद गर्नु पऱ्यो कुन कस्तै underscore यादै नभएको भने underscore t is equal to touch zeros len words in line len word to dictionary word in line. So for I word in enumerate words word in line word index 0 to index 3 nice. At this point, tensor represent one sentence of length 11 in an encoding space of size 207,261. The number of words in our dictionary. Figure 4.6 compares the gist of our two options for splitting text. Using the embeddings, we will look at the next section. The choice between character label and the word label in encoding leaves us to make a trade-off. In many languages, there are significantly lower fewer characters than words. Representing character has us representing just a few classes, while representing word require us to represent a very large number of classes. And in practical application deal with words that are not in the dictionary. On the other hand, word convey much more meaning than individual characters. Okay, so the representation of word is considerably more informative by itself. Given the stark contrast between these two, options. It is perhaps unsurprising that intermediate way have been found and applied with great success. For example, the byte pair encoding method starts with a dictionary of individual letters, but then iteratively adds the most frequently observed pair to the dictionary until it reaches a prescribed dictionary size. Our example sentence might then be split into tokens like this. Impossible. Yeah, but input character as old impossible. Okay. For the foremost thing, our mappings is just splitting by words. But the real part, the capitalized impossible and the name Bennett are composed of subunits, text embeddings. One-hot encoding is a very useful technique for representing categorical data in tensor. However, as we anticipated, one-hot encoding starts to break down when the number of items to encode is efficiently unbound, as with words in the corpus. In just one book, we had over 6,700 items. We particularly could do some work to duplicate words, condense, alternate spellings, collapse past and future tense in a single token, and that kind of things. Still, a general purpose English language encoding will be huge. Even worse, every time we encountered a new word, we could have to add a new columns to the vector, which will mean adding a new set of weights to the model to account for the new vocabulary entry, which will be painful from a training perspective. How can we compress our encoding down to a more manageable size and put a cap on the size growth? Well, instead of vectors of many zeros and single one, we can use vector of floating point numbers. A vector of say 1,000 floating point numbers can indeed present a large number of words. The trick is to find an effective way to map an individual word into this 100-dimensional space in a way that facilitates downstream learning. This is called embeddings. Okay, in principle, we could simply iterate over our vocabulary and generate a set of 100 random floating point numbers for each word. This would work. In with that, we could cram a very large vocabulary with into just 100 numbers, but it will forego any concept of distance between words based on meaning or context. A model using this model embeddings would have to deal with little structure in its input vectors. An ideal solution will be to generate a embedding in such a way that word used in similar contexts map to nearby regions of the embeddings. Now, if we were to design a solution to this problem by hand, we might decide to build our embedding space by choosing the map basic nouns and adjectives along the axis. We can generate a 2D space where axis map to nouns, fruit, okay, flower, dog, blah 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 blah. Our goal is to take actual fruit, flowers, and dogs and lay them out in the embeddings. As we start embedding the word, we can map apple to a number in the fruit and a red quadrant. Likewise, we can easily map tangerine, lemon, lychee, and kiwi to round out list of color fruits. Then we can start on flowers and assign rosy, poppy, daffodil, lily, and hmm. Not many brown flowers out here. Well, sunflower can get flower yellow and brown, and then daisy can get flower white and yellow. Perhaps we could update the kiwi to map close to fruit brown and green, and for the Wakalaya. One interesting aspect of resulting embeddings is that similar words end up not only clustered together but also having consistent spatial relationship with other words. For example, if we were to take the embeddings vector for apple and begin to add the subtract the vectors for other words, we could begin to perform analogies like apple, the red, sweet, yellow, sour, end up a vector very similar to one of the lemon. More contemporary embeddings models with birth and to making airlines are much more elaborate and are context sensitive. That is, The mapping of the word in the vocabulary to a vector is not fixed but depends on the surrounding sentence. Yet they are often used just like the simpler classic embeddings we have touched on here. Text embeddings are essential tools for when a large number of entries in the vocabulary have to be represented by numeric vectors. But we won't be using text and text embeddings in this book. So you might wonder why we introduce them here. We believe that how text is represented and processed can also be seen as an example for dealing with categorical data in general. Embeddings are useful whether one hot encoding becomes cumbersome. Yeah, indeed, in the form described previously, they are an efficient way of representing one hot encoding immediately followed by multiplication with the matrix containing the embedded vectors as rows. In non-text application, we usually do not have the ability to construct the embeddings beforehand, but we will start with the random number we squeezed earlier and consider improving them part of our learning problem. This is an standard technique, so much so that embeddings are a prominent alternative to one-hot encodings for any categorical data. On the flip side, even when we deal with text improving, the pre-learned embeddings while solving the problem at hand has become a common practice. When we are interested in co-occurrence of observation, the old embeddings we saw earlier can serve as a blueprint too. For example, recommender system customers who like our book also bought that are use the items the customer already interacted with as the context for predicting that what else will spark interest. Similarly, processing text is perhaps the most common. Will explore tasks in dealing with sequences. So, for example, when working on tasks with time series, we might look for inspiration in what is done in natural language processing. Conclusion: we covered a lot of ground in this chapter. We learned to load the most common types of data and save them for consumption by neural network. For course, there are more data formats in the world that we could hope to describe in a single volume. Some, like mathematical histories, are complex to cover here. Otherwise, like audio, video, where them seems crucial for the path of this book. If you are interested, however, we provide short examples of audio and video tensor creation in bonus chapter provided in this book website. Okay, and in our code repository with the LPT code master PL chapter 4. Now that we are familiar with tensor and how to store data in them, we can move on to the next towards the goal of this book. Teaching. Oh, sorry. Now we are familiar with tensor and how to store that in them. We can move to the next step towards the goal of this book, teaching you to train deep neural networks. The next step will cover the mechanics of learning for simple linear regression, simple linear model. Summary: neural networks requires data to be represented as multi-dimensional numerical tensor after 32-bit floating points. In general, PyTorch expects data to be laid out along specific dimension according to the model architecture. For example, convolutional versus recurrent. We can receive data effectively with the data PyTorch tensor API. And thanks to how the PyTorch libraries interact with the Python standard library and some surrounding ecosystem, loading the most common type of data and converting them to PyTorch tensor is convenient. Image can have one or more image channels. The most common are the red, green, blue channels of typical digital photos. Many images have a per channel bit depth of 8, though 12 and 16-bit per channel are not uncommon. This bit depth can also be stored in 32-bit floating point number without loss of precision. Single channel data format sometimes omit an explicit channel dimension. Volumetric data is similar to 2D image data with the exception of adding a third dimension depth. Okay, and the converting spreadsheet to tensor can be very straightforward, categorical, ordinal valued. Columns should be handled differently from interval valued columns. Text and categorical data can be encoded to a one-hot representation through the use of dictionaries. Very often embeddings give good, efficient, and representation. The mechanics of learning, next chapter 5 भोलि हेरिन्छ. आजलाई बाई बाई, यति नै हो.